Okay, thank you for the introduction. So I'm going to talk about Silo. So Silo is a network sharing solution for multi-tenant data centers, including public cloud data centers like Azure or Amazon EC2. So these cloud data centers, just like other data centers, have servers and network fabric connecting them. And users rent virtual machines, and provider allocates resources for virtual machines. And users run their application which generate traffic between servers. So important fact here is that many users will share the resources, including network, CPU, disks. And resource sharing is great in that it increases the utilization and perhaps increase revenue and decrease the cost. However, sharing can also affect the tenant performance, and this applies to all the resources. But in this work, we focus on the network sharing part. So first, I'd like to demonstrate the network sharing is a problem with the simple experiment. There are two tenants sharing the cluster of 5 machines. Each tenant has 15 virtual machines as shown on the left side, and one tenant is running Memcached and the other is running NetPerf. We measure the latency of the Memcached workload with and without the NetPerf tenants, and here's the result. And as you can see, latency has increased significantly with NetPerf tenant running. So the latency increased by a factor of 9 at median and 99th percentile, and at higher tail, it even suffered from TCP timeout, resulting in 200 milliseconds. So obviously, if we share the network, the performance will be worse. But the problem with today's cloud is that there's no SLA for the network. So what do we need to do to solve this problem? First, we need a predictable network performance across applications that have different network requirements. So here I'm showing the application in two-dimensional space, based on how latency sensitive they are and how bandwidth sensitive they are. So applications like MapReduce are sensitive to the bandwidth requirements, but not much in terms of latency. And message-driven applications like online game servers are very sensitive to latency, but doesn't require much bandwidth. And there are OLDI applications like search workload, which are both sensitive to latency and bandwidth. So what we want is to provide a predictable performance across all different range of applications. And second, the network performance should be independent of the other tenants. So what it means is that no matter what other tenants are doing, a tenant's worst case performance should be bounded. So, of course, this is not a new problem, and many existing solutions are out there. So given that, why is there another SIGCOMM paper this year? So for our purpose, we look at 3 criteria. So first, whether they offer predictable network latency. We don't show bandwidth because it is a well-studied problem. And second, do they support multi-tenancy? And third, do they require any changes to hardware or tenant application? So I'm grouping many existing solutions into 5 different categories in each row. None of the existing solutions satisfy all these requirements, and that's what Silo is trying to solve. So to meet those criteria, we look at application behavior through the lens of message latency. So what I mean by message latency is the unit of data transfer for a given application. So for example, when you look at the MapReduce jobs, a message is a block of data, which can be huge. On the other hand, for key value store like Memcached, a message can be a key or value which is as small as few bytes. So therefore, different applications have widely varying message sizes, and we assume a tenant can determine their message size and their desired SLA. So given this information, we'd like to provision the network to meet this SLA, and this is achievable by providing the predictable message latency. So now I'm going to explain how to achieve predictable message latency. First, I would like to define the scope of predictable message latency. So from the application's viewpoint, the message travels through many layers of software and hardware, and delay in each layer adds to the message latency. So Silo focuses on the network. To be precise, its guarantee is from sender sneak to the receiver sneak. So now let's look at the message latency in the network. So first, is the transmission delay, or message type divided by bandwidth. And second is the queuing delay in the network. So I'm omitting the propagation delay because within the data center, they're typically small and bounded. So based on this observation, we can derive two requirements for predictable message latency. So one is minimum bandwidth should be guaranteed, and the second is maximum packet delay should be bounded. However, just bandwidth and packet delay is not enough. So suppose we have an application that generates 100 kilobyte message every 2 milliseconds, and we want the message to be delivered within 1 millisecond. In this case, if we guarantee the instantaneous bandwidth to be the same as the average bandwidth, 4 megabits per second here, then each message will miss the deadline every time. On the other hand, if we had allowed burst of 100 kilobytes at 1 gigabits per second occasionally, then you'd meet our SLA requirements without increasing the average bandwidth. So in reality, data center traffic is not uniform, and it has burst arrival, and this is another reason that we want to make sure that we can observe burst. So to recap, we want to provide a predictable message latency, and we derived 3 requirements for this. So now I'm going to explain how to achieve predictable message latency in networks. So Silo relies on 2 key mechanisms to achieve predictable message latency. So first is the traffic policing at the end host, and we do not require any changes to the network. I explained the network abstraction we provide for the tenants and how we enforce it. And second is the placement to guarantee the network requirements for all tenants sharing the cluster. So placement does not, placement also does the admission control, so it will reject requests if it violates the guarantee for itself for any of the existing tenants. So in the past, many work have looked at the providing bandwidth guarantees, and many of them build on the host model, which provides the bandwidth as if all VMs are connected to the single switch. So Silo extends these guarantees by providing guaranteed latency between virtual machines and allowing the burst arounds per virtual machine. And by latency guarantee here, we mean the per packet latency guarantee between 2 VMs. So given the network guarantee, we pace the traffic to enforce it. So all VM traffic is first sent to the Silo pacer at the hypervisor. And inside the Silo pacer, we have layers of token buckets. First, we have a token bucket per destination VM, and this token bucket layer ensures the host model guarantee. And second, we have another token bucket which enforces the aggregate bandwidth and burst from each VM. And we strictly limit the guarantee, meaning our guarantee is not work conserving across tenants. So one challenge with the pacing is that network stack in the software typically use batching to achieve high throughput and low CPU utilization. So software pacing is typically coarse-grained and inaccurate. So let's first see what happens when you just use coarse-grained pacing. So in this example, VMs use batching, which typically operates at 64 kilobyte chunks, and the hypervisor paces at this granularity. And even with the pacing, the VM might still send 64 kilobyte microbursts. And these microbursts can be problematic. So for example, in this case, 10 VMs are sending to the one receiver through a switch with 300 kilobyte buffers. And buffers will overflow, resulting in packet drops. And this can happen even when the sender is ready to 1 Gbps and the aggregate rate is less than 10 G. So to solve this issue, we use void packets. So suppose there are 2 VMs, one with the 2 gigabit rate limit and one with the 1 gigabit rate limit. And we want to achieve the packet level pacing. So when Silo pacer receives it, it creates a batch of packets that is paced with the void packets. And it sends out the both data and void packets to the NIC as a batch. Then the NIC will send out both of these packets. And when it is received by the first hop switch, the void packet will be dropped and only the data packet will go through while maintaining the packet gap between data packets. And such void packet can be created by having source and destination MAC address to be the same. And so by using void packets, we can keep the I/O batching while pasting the packet at a finer granularity. So now I'll move on to the VM placement. So there are many existing VM placement techniques to guarantee the bandwidth, but those are not sufficient. And here is why. So let's consider these two example placement. There is a tenant with 9 VMs, 1 gigabit per second per VM with 100 kilobyte burst allowance. And the server is connected to switch at 10G, and switch has 350 kilobyte buffering. So I'm showing two different placements, and both placements satisfies the bandwidth requirements. However, they differ in terms of maximum queuing occur at the switch. So in the worst case, left side would require 400 kilobytes of queuing. On the right side, it would require 300 kilobyte queuing. So on the left side, it will suffer from the packet losses. And Silo uses network calculus to find the placement that bounds the queuing delay and prevent such packet loss. So what we want to know at the placement time is that how much queuing can happen for a given placement on each port. So suppose we want to know the amount of queuing at the output port of the switch on the blue link shown for the given placement. So we can generate the worst case arrival curve based on the VM's network requirements, as shown on the right side. And we can also generate the service curve based on the switch link capacity. And by looking at the difference between these two curves, we can determine the maximum queuing that can happen on the rightmost port. So we have more details in the paper with some optimizations and complex cases. I'm not going to go into details. And Silo's VM placement is greedy heuristic. It's similar to prior work. So for a given tenant request, we generate a placement and we check whether it meets the constraint using the network calculus. And if those constraints are not met, we move on to the next placement. And at the end, if we cannot find any placement that meets the requirements, we simply reject the tenant request. So now I move on to the evaluation. So we evaluate Silo using 3 ways. First is a small-scale testbed experiment using Memcached. And second, we use a packet-level simulator to compare against the existing solutions. And finally, we use large-scale simulation to quantify the network utilization trade-offs. So testbed experiment is the same experiment as the motivation experiment I showed earlier. We have 2 tenants sharing the 5-node cluster connected to 10 gigabit network, and one running the Memcached and the other running the NetPerf. And we run Memcached based on the Facebook's published workload. And NetPerf generates the bulk TCP transfer modeling the shuffle phase of the map reduce. So now I'm going to show the tail latency at 99 and 99.9 percentile for Memcached tenants. But for Silo, we provision the network such that it gives 2 millisecond guarantee for Silo. So to do so, we measure the Memcached running in isolation and use the throughput and packet size observed from the run to provision the network. So here's the result. Blue bar is with Silo and the red bar is without Silo. And at 99 percentile, Silo improves the latency by a factor of 4 compared to not using Silo. And at 99.9 percentile, without Silo, it's suffered timeout, while with Silo, it still stays within the guarantee of 2 milliseconds. And we find that NetPerf tenant achieved 93% of its original throughput when running in isolation compared to when using Silo. And this is exactly the bandwidth we provisioned for the Silo case. So Silo allows us to trade off the utilization to get the predictable performance. So next is the packet level simulation using NS2. So we target medium scale by modeling 10 racks and 40 servers per rack and 8 VMs per server. So total 400 servers and 3200 VMs. We emulate the cloud workload by randomly generating two types of tenants. So class A tenants are latency-sensitive tenants modeling online search query traffic. So it repeats the short messages with all-to-one communication pattern. And there's class B tenants, which are bandwidth-sensitive tenants modeling the data pattern application. And we use parameters on the table and generate the parameter for each random tenant using the exponential distribution. So we compare Silo against several cases. First is the TCP for the status quo, and DC-TCP and HER are both low latency transport using the switch ECN mechanism. Octopus is the bandwidth guarantee network sharing solution, and Octopus Plus is the extension that we made to Octopus to allow the burst sending. And we use different placement algorithm for each of these cases. So for TCP variants, we used packing placement or locality aware placement because they are not aware of bandwidth guarantee semantic. And for Octopus, we use the bandwidth guarantee placement. And for Silo, we use both bandwidth and delay guarantee placement. So the difference between Octopus Plus and Silo is only in the placement. So first, we look at the message latency for class A tenants, which are latency sensitive. So x-axis here is message latency in log scale, and each bar represents different schemes. And in each bar, we show median, 95th, and 99th percentile. So Silo has much lower latency than all other schemes at even at high tail, and we also confirm that it meets its predictive message latency guarantee even in the worst case. And Octopus is much slower because without the burst allowance, it needs to spread out the packets for one message over a long period of time, if the bandwidth is low. And Octopus improves the delay over Octopus by allowing burst. However, it still suffers from TCP timeouts because there's no delay guarantee at the placement. So next, we look at the class B tenant, which is bandwidth sensitive. So the graph shows the CDF of the relative message latency against the estimate using the bandwidth requirements for a given tenant. And in this case, both Silo and Octopus completes its message exactly at the predicted time. And the reason that Octopus also does well is because it's bandwidth sensitive and packet delay does not affect much. TCP and HER, which gives the fair share, performs slower in some cases due to the if there's many contending traffic, then you could get lower bandwidth than what you expect. And in some cases, it's actually better than Silo because it's work conserving and you can use more bandwidth if it's available. So next, we look at how bad is the network utilization for Silo, given that it's not work conserving. So I'm showing the network utilization for 3 different cases here. So this result is based on the large scale simulation instead of NS2, large scale flow level simulation instead of NS2, and we plot the overall network utilization across varying target occupancy of the data center. And interestingly, TCP uses the least amount of the network. And this is because we used packing placement or locality aware placement, which naturally reduced the traffic in the network because they put as much VM as possible on the same server. And compared to Octopus, Silo has 11% lower utilization in the worst case. And this difference comes from the fact that Silo rejects the requests when it cannot meet the delay guarantee. So this is cost Silo is paying to give the delay guarantee. So to summarize, we developed Silo, which ensures predictable message latency. Unlike today's cloud, where latency-sensitive workloads will suffer from the bandwidth-hungry tenants, Silo can enable them to coexist and still give the predictable network performance for a wide range of applications. And we developed several techniques to enable this. So VM placement that is aware of both bandwidth and latency guarantee, and fine-grained software pacing. And Silo does not require changes to network or tenant stack to get the predictable network performance. So Sorry.
So questions?
Mia Kuleman, ETH. Hi. So maybe I missed this part, but how do you get the information what the requirements of your cloud application are? Like how much bandwidth your application needs or how much latency the application needs?
So that's a very good question. So in our test, we run the application in isolation and measured it, but I understand this may not be practical option in many cases. There has been work automatically. So there has been prior work on automatically deciding the bandwidth guarantee part, and I think similar technique might be able to useful to deciding the network latency guarantee part. But for silos perspective, we assume that tenant can specify the requirements.
Ehsan Kazi from LUMS. So I was wondering, so many data center switches have shared memory buffers.
Yes.
So I was wondering how would this function with, when you have one shared memory buffers and other is contention at different ports.
So
and sorry, heterogeneity between buffer sizes.
So we did not model the shared memory part in the current implementation, but that can be modeled. So basically, we have a queuing capacity on each port that's fixed, but at the placement time, we can actually look at all the amount of queuer that are used in the worst case, and then combine them and compare against the shared buffer to actually model the shared buffer switch. So that's certainly doable. I'm sorry, I missed the second question.
The second question was if there is heterogeneity across buffer sizes in switches.
Yes. Well, so we model it as basically we model queuing capacity as either switch buffer size or the network the requirements that like application gives. So we can model any of those as a parameter in the system, so it'll work fine.
Hi, Eric. Hi, Eric Rosner, IBM Research. Over here, middle.
Oh, okay.
I was wondering just kind of what's going on underneath the covers. Did you have to disable TSO on the hypervisor to get the pacing packets to work?
So we do not use TSO at the NIC driver level, but we do enable TSO on the VM side. So VM can still send the packets with the batches. We segment them at the hypervisor level, and then we create a batch of packets, including the void packets, and then send it out. So we do the I/O in batching, but do not use TSO.
Okay, maybe we should talk offline more, but I guess I'm wondering then, like, what sort of tricks, I guess you said batching to get it to work at 10
Yes, so there's definitely performance penalty that we are paying for disabling TSO. So this is the CPU overhead of our pacer, but it can be much further optimized. Basically, we pay about 60% of CPU cycles for simply generating void packets with the MTU sites. And if you have 9 gig of traffic, we have to put 1/10 of MTU sites between each packet. And in this case, we put about 20% of the one core on top of the original network performance. But these are all measured without TSO enabled. So if you compare against the TSO enabled, it might be with TSO enabled, the average CPU utilization on the blue bar might be much lower actually.
Okay, thank you.
Yeah.
Okay. Do you consider the delay guarantees across a hierarchy of switches or just at a single switch?
Oh yes, we do consider against hierarchy of switches.
Okay, so your void packets are going to get dropped at the first switch.
Yes.
So after that, you're going to get some delay jitter. You're going to get some jitter in the packets, right?
Yes.
And so when you aggregate up these at the next level, you're going to have a arrival curve, which is going to be difficult to model.
Yes. So the reason that we used void packet in the beginning is because software part is very jittery. So, but I believe hardware switch is maybe somewhat jittery, but much less jittery. And another thing is, as the flows travel through the switches, the other flows can affect how bursty you are for a given flow.
Yes.
And we model that assuming the worst case. So we have more details in the paper. Basically, we model any impact that one flow can make to the other in terms of burstiness.
And so you figured out how to use network calculus, deterministic network calculus to do the modeling of the departure brackets?
Yes.
Okay. All right.
Okay, so let's thank Hong. And